Hey guys, it's Eddie the Grouch, the Tightwad Tinkerer. Today, this is going to be a real quickie. I just got back to my vacation. I was a week enjoying the sights with my family, all 10 of them, and I really couldn't wait to get back. Anyway, I'm catching up on my videos, and I see Blue Hands was working on some bearing adapters, and he was running into a phenomenon with CNC and older machinery that I wanted to touch upon. I think he got it straightened out in a later video, but I really couldn't resist the urge to obfuscate and totally confuse the hell out of you. So let's move on. Let's see what happens and what maybe can be done about it. So in his example, which I'm not going to do because I don't have a whole lot of material, I can well, I do have some conduit. Maybe I'll chuck some of that in there, but in case I don't, here's what's happening. He had some, well, let's just find something as an example. He has some steel tubular pieces. I'm going to use this piece of EMT. Oh, they're about an inch long or so. And he wanted to do a cutoff and cleanup operation on these bits here. So he needed 0.7 or 7 thousandths on the length of these. So he would chuck these up. It would, with his smaller chuck, it would act as a backstop, and he had enough outside the jaw, so he programmed a small G-code program to basically do a hit and run. Zoom in, cut the part off, get the hell out, and then he could re-chuck a new part in there. So the code is simple. We'll run through it real quick. Basically, it'd be at his tool change position. It would zoom over, do a cut, wrap it back out. So the problems he was having was after the cut, he had a lot of flashing on the inside of his tube there, and his cuts were not being consistent. He was not getting that 7 thousandths target repeatedly. So I wanted to get into the mechanics of it, so in case any of you other beginners like us, because I believe we're both pretty new at this, Blue and I, so we're fumbling through together. And we're using Mach 3. Now, I'm not saying it's a bad program. It's an excellent program for the beginner, but it does have a limitation, and that is it's a Windows-based program. Windows does not like to give you direct control over anything. So the creators of Mach 3 went through a lot of contortions to make a driver that would interface with the parallel port directly and get the timing down to where it would be repeatable. But Windows goes off and does its own thing, whether it be file cleanup or indexing or just sitting in a corner and picking its nose. It's going to lose some clock cycles, and unless Mach 3 can compensate for it, you're going to run into maybe a lost step or a hiccup or something like that. And that increases the higher you increase the clock rate. The default clock rate on Mach 3 is, I think, 25,000 cycles or whatever they use for a rate. And I'm running 35 because I have another couple motors being used simultaneously, and I needed the I need them to do these things at the same time, and I believe Blue is doing something similar. So that might play into it, but we're gonna take Mach out of the equation. Just something to keep in the back of your mind. If you have your computer doing anything else while running this program, things could get disturbed on the signal end, on the controller end. So taking the controllers out of the equation, let's look at the mechanics. Okay, let's address the flashing he had on the end of his tube. I think the problem he had there was the cutter. Now your basic turning cutter is going to be like this, probably, if you're using an insert. Especially if you're using an insert, it's going to have a radius, and that's, that little tiny curve at the end. So when this is pushing, it does push before it cuts, because it's sort of got to get the metal under compression, and then when it gets there, it's actually pushing that little bit of metal inside, inside that radius. So as he's cutting straight across, it's folding over and creating that flash at the very end. So the way around that is just to use something really, really sharp. Use your cutoff tool and angle it a little bit, or actually it's better to be grinding it. Heck, it's easy to dress up a cutoff tool, but he's using indexing. But if you're using a standard high-speed steel cut-off blade like this, just cut you an angle. Oops, I don't know how to keep getting out of frame. Just cut an angle. Let's see, how would we show that on TV here? Do I have anything flat besides my head? If you put an angle like that on the edge, that means the top edge is going to be your lead, or when it's mounted, it's going to be your left edge, and that will cut into the part and shear it off without any flashing. If it's angled the other way, you're going to have the same problem you have with a radius tool. So that's one way to get rid of that. Maybe make yourself a special cutting tool. Here's a little one I've got. See, that's sort of like a knife edge right there, and there's no radius in that, and I use that for threading up to a shoulder when I gotta do a really dinky thread. And you come in with that little point and stick it at an angle to make sure that point, the very tip of that tool, is cutting your metal and shearing it, and you get in there and you get a nice clean cut. You go off to the edge, you know, away from it or any other angle, you're going to push the metal rather than cut it. So you want the very leading edge to be doing your cutting and scribing, and that'll get rid of most, if not all, of your flashing. So that point's done. The next thing was his repeatability. Now this is an old-ass machine. This is an old Smithy 3-in-1. I believe it's a CB 1220, which means I have a theoretical swing of 12 inches and a 20-inch bed. Or 20-inch usable center-to-center area. Now the problem with this particular machine, and maybe some others, is that's a huge ass cross slide, and that's going to come into play with the three other things that's going to affect your repeatability outside of your controllers. Purely mechanical, one is going to be momentum. So you've got a little slop. You're going to have two areas of play, maybe three. I'm getting ahead of myself and talking really fast. Let's see if we can address these. Let me zoom back out here, get these cans out of the way. So your machine has to be absolutely rigid to get repeatable results. That's why they're called precision machines, and why really precision machines are so much bigger. Everything's got to be super rigid. So on a small machine like this, there's going to be some shortcuts. So let's put this in manual here, and we'll go slow motion. So you're going to have, oh, gotta move the camera now to show you this bit. Okay, we're going to come around here. Here's the backlash and the slop that most people are familiar with. That is in the lead screw. Now you can see I can turn that quite a bit, and this table's not moving. See how the threads are going in and out of the nut? That is your classic backlash. Put you back on the thing here so I can use both hands, because I like to pick my nose while I'm working. So that's going to affect how much slop you're going to have. Now that's going to come into play along with momentum. So you're in a rapid move. You are zooming down the table, and your motor slams on the brakes. Well, this heavy thing, if it's in a fast enough move, is going to keep going forward, and that's going to throw off your measurement. That also applies with your cross slide. So you're zooming along, slam on the brakes. If you've got any play in a cross slide, you can see I have quite a bit there. So you wrap it in, slam on the brakes, it continues to go, boom. Now in his particular scenario, since it was a cutoff operation or a parting operation, it would have no effect unless he didn't go deep enough with his G-code to get all the way through the cut. But that is going to have an effect on your turnings, your facings, and everything else. And because this is also a mill, well, it screws everything up. So unless you've got that addressed, you're going to have that problem. But with back to Blue's issue, okay, that's your second bit of slop. So you've got your Z going forward and back, or excuse me, well, left and right, and you've got your X going forward and backward. So if those aren't acting predictably, you're not going to get a predictable result. And the other one is your ways. Now I've loosened mine up a little bit to exaggerate the principle, but you know, follow along here. We're gonna go in deeper in this, but this is just to give you the overview to see if you want to continue watching this stupid video. I've got a lot of crap on the back end of mine because I decided to put my motors in back so it's out of my way, because I like to use this as a manual machine as much as possible. When I keep screwing up or I have a lot of things to do, then I'll, you know, turn on the controllers and let it do its thing. So, but I really prefer having the manual controls out here. That aside, so you're cranking along again. You're zooming down in a rapids towards your headstock. Slam on the brakes. Not only is this piece sliding forward, your slop in your ways is going to kink your table side to side. See that movement there? I'm going to move the camera again to show that just a little bit better. Yeah, my computer really chokes on these files, so I'm not editing a lot out. So please bear with the dizziness. Okay, you see that kind of play there? So that's going to add another unpredictable movement. So even if you get the slop taken out of your lead screw, this will hold this end steady. When you slam on the brakes, this one's going to swing forward, and depending where your blade is on the table is going to see how far off you're going to be from your chosen measurement. So if you're farther back here, you're going to have less of a hinge effect, because this becomes your pivot. Wherever that lead screw is and your ways, that's going to be your pivot point. So if you're on the pivot point, your blade should technically stay okay, but it's going to cock. If you're over here and you've got this table wound back and you're doing the same thing and you slam on the brakes, oh hush, excuse me, damn it, just like a woman, always bothering me at the wrong time. Okay, where was I? Okay, when your controller hits the brakes, this end's going to swing around. You got some swing in your thing, and when it does that, well, that's easily a couple of thousands. That's going to throw you off. So I'm going to pull a chuck out of the way. We'll put a couple indicators on here, and we'll get some numerical evidence, and then we'll see about getting rid of some of it, sweeping it under the carpet, so to speak. Okay, that furnace finally shut off, and we can continue with the obfuscation. So we're set up with a couple of indicators, and oh, this is my table, a cross slide. I really would have preferred to use 2 clockwork indicators because I like seeing the swing, but that's the only one I got. So I got the digital one over here, and it's going to read a little bit different because it is electronic, and it's going to have an averaging algorithm in there to get a number playing with that little 5 spot over there, but hopefully this will show some stuff. So I just got the table sitting here at rest, and we're going to look at some of the slop here. Okay, one of the slops is of course the lead screw. That is the only one that CNC machine cam programs can compensate for, because you can sort of measure it, dial it in, enter the numbers, and it'll do its best to compensate for that. It cannot compensate for the ways, or the weight, or the momentum of the motor and the table. So sitting here, see, they're both pretty much zeroed out. So I'm going to bump this back side here. I hope you can. I'm going to bring this back a little bit. Hopefully, oops, you can still see the gauges. So I'm going to bump this side of the table. Wow, that's 9 thousandths right there. And the other side shifted 8 thousandths. Okay, let's try to hold this side, and we'll play with this one over here. Oh, look at that, 20 thousandths. Yeah, I do have my ways a little bit loose to illustrate the point. So, like I said, you're zooming along on the rapids, and you hit the brakes. That back end's going to swing around like a jackknife semi, and that can make a little bit of difference. Of course, not that much difference. If you're running a table this sloppy, well, you need some of those Adam Booth's big boy tools to play with. So, those are your three areas: your lead screw slop, your way slop, and I know there was another one, and your momentum of the motor. So if the motor can't stop dead nuts, it might go another step, depending on the friction of your table. It might, you know, stop right on or stop a step short. So if you, depends on how fast you're going, how fast you're rapiding, well, how fast you're zooming along on your rapid command, the weight, and the friction that you're overcoming, the drag of your table, your ways, because your weight is resting on this surface here. So how well that's oiled is going to come into how much drag you have, how tight you have your gibs, that's going to factor in. How heavy this honking beast is, that's going to factor in. And of course you're going to have your tool pressure if you have any. So, you know, your different tool pressures is going to affect how your table moves around when it's sloppy. So you're doing a facing cut, it's going to push back on it. And if you're doing a facing cut in aluminum or a drilling operation, well, you might be sucking that table in. So this is where the rigidity is the key. It's the only way you're going to get any precision work done. And as you can see, I get absolutely no precision work done whatsoever. But it sure beats working on a drill press. So let's try to address some of this stuff. Actually, I should run the code and see if we can get some variances and see how it plays out. So we'll call that, well, 0 for the most part. And I'm going to zoom out and zoom back in, and we'll do some playing and see how it comes out. So we're going to step through the CNC. Okay, so step through, single block mode, wrap it in. Okay, that didn't come out too bad at all. But your table's not going to be worn in the same place, or excuse me, evenly, of course. So say you set your gibs up back here, nice and tight, you got as much slop out as you can. Well, you get into the sweet spot where the machine spent most of its life, it's going to be looser there, and you're going to introduce some errors. So if you have a repeating operation like this one, get your tool up where it's going to be, and then do your dialing in. Get your slop out as much as you can, and then, you know, hopefully it'll be all nice and copacetic at the point where it actually counts. So I'm going to run through that a couple of times. I don't have a whole lot on here. I guess we can add some weight to the table and see how that might affect stuff. Let's see. Let's throw this angle gauge on here, or angle plate. This is a few pounds. Let's put that over there. See if that affects anything. Hey, this is see the pants stuff. I don't care if it's accurate, I just want to make noise. Okay, do our cut. And then we'll swing back. Okay, let's try it again. Okay, looks like it lagged behind this time by 1/1000. So it added drag, did not add momentum. Okay, it's still a change, and it's still bad for you. Change is bad, remember that. Come back. Okay, let's try to take some of this slop out and see what happens. I do have a wrench somewhere for that, don't I? Okay, so we're going to deal with that mess right there. I'm going to tighten up the gibs. I'm sure I'll screw that up, because these ways are pretty atrocious. And I don't want to get too much. Also, you're going to have, I don't know if you call it cogging or what, but your steps. If you've got your steps set to a coarse value in order to get some really good rapids, well, you're not going to get that fine-tuning granularity. So one step can be 2/1000. And, you know, like I said, one burp in windows can throw you off 3 or 4 steps because they're working pretty darn fast. So you want to take that into account. You might have to slow down your rapids or your fastest speed in order to get the precision. So each step of that motor. Now mine is geared where I've got a slow turning shaft, so it's like maybe a 3-4 to 1 ratio, but I'm heavy on the motor side because I want the torque. Stepper motors do best slow speed, and because it generates the most torque. Higher speeds is when it starts cogging and losing steps. So since I'm heavy on the motor side, that little bit of movement can translate to, you know, quite a bit when you're geared down like that. So that's also something to keep in consideration. Okay, so I've tightened these up. Darn it, I can't really test it because then I can't on motors. I hope that's not too tight in order that the motor cogs. We'll find out, because it's really hard to judge without moving the thing back and forth, but I can't do that without disengaging the servo. So we'll just double check this here, make it snug but hopefully not too tight. Let's see if we took any out. Okay, there's a little bit left in there. See if I can get that little bit more. Hopefully the motor will overcome that. I really need to scrape in these ways, but my problem is I don't have a straight edge long enough. So until I obtain something like that, so I can start working on these and get a nice smooth symmetrical distance between the ways here, I'm never ever going to get any kind of precision. So until I get the little hourglass shape out of here where it's worn right about here, because I get over here it gets tight, I pull back it gets tight. So if I dial in here where it's nice and smooth, I go to pull out, it jams up. So I really have to get that addressed, but the machine's just not worth sending it out and having it fixed. And you know, anywhere I send this, they're just going to laugh at me unless they charge a lot to make up for all that laughter. So anyway, enough rambling. Let's try this again. I really got to move the machine closer, or should I say the computer closer. Okay, with the Gibbs tightened up, now I'm -2 on one side and I'm +3 on the other. Okay, so let's zero that out and see how repeatable that is. Okay, Fred, one more time. Nice. Much nicer. In my opinion, with that sort of operation, I think this is the most critical. If you can keep your table parallel with the ways, that is a lot more important to me than the lead screw. The lead screw you can mentally compensate for. Manual machinists do it all the time, but it's really important to have that that cross slide staying as steady as it can be, because that'll also introduce chatter. It just gets ugly. And just like a loose bolt holding something together, the more that's loose and it's hammering around, the more you are actually putting wear in the machine. And then we can also get into lubrication thickness, you know, getting squeezed out, sucked back in, throwing off measurements. It's small, but it does all add up. Okay. That really ain't too bad. Well, okay, yeah, it is. Look at that. I got 9 thousandths that way. Okay, that's my lead screw slop. Let's where are we at on that table there too? This is not a rigid machine at all. I just want to make sure if they're both going in and out at the same time. Let's re-zero this and check. Of course, this magnet slides a little bit. I really have a horrible setup here for demonstration purposes. Okay, pulling back. I got -8 there, and I got -9 on that side. Let's push up. Okay, +2, +1.5. Messy, messy, messy. But I'm staying within, you know, a thousandth or two between the two. So I'm mostly parallel. We're mostly seeing the lead screw slop. So let's get this damn thing out of the way. And we'll do some torquing sideways. Okay, so 1 there and -2. So I have a 3 thousandths twist. Okay, back over here, -2 + 1. So I still have, let's tighten up just a little bit more. And with these coarse screws, it's really easy to overshoot. And I really need to tap this out for a finer thread. And I really need to get on these ways. Okay, now let's see what kind of mess we got. Okay, bump it all the way up. 0. Damn thing is moving on me. Well, it doesn't help that that's loose, does it? And like I said, this is a pretty crappy setup I got here. Okay, I got 7 thousandths, which I knew. 7/8 thousandths in my lead screw. Okay, 0, 0, 8, 9, 8.5, 9. Okay. Now, you can't use these numbers for dialing in your compensation because you don't know how much drag you're going to have during operation. So you may think, okay, the maximum backlash I have is 8 thousandths. But you're cruising along, and if you're doing a slow movement cutting into a part, well, maybe the cutting pressure is light, and the humidity is just right, and the moon is smiling upon you, and you're not getting as much drag as you normally would. Well, you're not going to be pressed all the way up against your limit, so your backlash, your operational backlash, may be only 4 thousandths. So that's why rigidity is such a key. And if I really understood that before I got into this whole damn expensive ass hobby, I'd have held out for something a little nicer. But I'm a glutton for punishment, and I'm going to make a silk purse out of a sow's ear one of these days. So I learned some scraping. I'm going to get that dialed in. I'm going to change this square thread over to balls. I don't know. But my key thing is I still want to keep manual control because machining is fun. Believe it or not, despite all my cussing. And I'm sure Mike's probably did some cussing too, but he's got 2 machines, so he's lucky there. I just got one piece of crap that I'm trying to make do everything, and as everyone will tell you, you just can't do it. I'm going to try to get close. Reinvent the wheel, that's my motto. If you can't get it right, get medieval. That's another good motto. Alright, so, how much corkscrewiness we got in here? Okay, visually you can see a little bit there. Okay, plus I have my in and out play. But to adjust that, I got to pull this motor off, pull this end plate off. Oops, you can't see that, can you? I got to pull this off, and my half nut somewhere in here. And I got to take a long ass screwdriver in through a little opening and try to tighten that down. That's one I really want to convert to a ball, just for the fact that I don't like going back in and out of there. So I'm going to take a hair off that side to side. Now, most operations, that little side to side is not a big deal. You know, manual machinists deal with it all the time. When you get in the CNC and you're thinking that's the be all end all to precision, that you find out it falls apart. But we're adventurers. Okay, I'm going to leave it at that, and see if I still get travel. Let's grab the pendant here. Ye old high-tech pendant. Okay, I don't see a whole lot of visual shift there, but then again, oh, there's a little bit, or I'm imagining it. But we're going to say that's as good as I'm probably going to achieve with this setup. Okay, now let's take out some of the other slops. So we did what we could with this. That's the important one as far as I'm concerned. Now we go and trip on cords and bump the tripod in a whole bunch of crap here. I'll try to cut that out. Okay. Here's my oh so cheesy lead screw. And for some reason, you really can't see it, can you? Okay. Yeah, the light behind me burned out. Brand new light. And I don't know whether to fix it or bitch, but I let it sit in the box too long to clean that out. Whoa! Yeah, that's what happens when your cords are overhanging your handles. I hope you all enjoyed that ride. Where are you? There we are. Okay. Use this, see if we can get a little more light in there. Okay, here's my pissy ass adjustment. This is just a bronze block. It's got a split in it, and this bolt here rides through, and it pinches the threads together. You got the main thread on the fat portion of the block, and you've got 3/8, probably less than ½ of an inch on this we'll call the tab. And then you squeeze those together and it takes some slop out. It's not ideal because your threads are cocking, but what are you going to do? It's junk. So that is well, I don't know what it is. Let's use pliers. Still a lot of play in there. Now, this one's not super important, but for the operation that Mike was doing on those pieces, yes it is. Unless you're compensating for it. I wonder if I got all that out of there that I could. No, that nut don't look that squeezed. I might have put Loctite on that thinking it would be a good idea. I'm not getting much movement out of that. Okay, let me find a socket. Okay, remember this all ties in together. So if you have the loose gibs, you have a table with a sway back in it, or belly, or whatever it is it's called. See, now it's taking out some slop, but it's also getting tight before all the slop is gone. That's because the threads are getting cocked. There's really got to be a better way to do it with square threads, because you can't pinch in and ride those angled crests. You basically have square threads. So the only way you can remove backlash is by squeezing together or apart, and that kind of bites. All right, I guess that's all I'm taking out right now. Okay, what was I saying? Oh yeah. So in a setup like this, where you have your rigid half nut and you've got crappy square threads, or I guess any threads with a long, okay, stop calling it a half nut. It's a block. I guess I'll call it a half nut. It's a whole nut. My nut is long. Remember that, folks. So if you got a long nut, it's rigidly mounted. You're on a shaft that's, well, it should be rigid, otherwise you're machining with noodles. And this table cocks. Well, now your threads are cocked down here, and it's going to bind on the sides. That plays into it. See how it's all interrelated, kids? It's a wonder this shit works at all. Okay, can my motor overcome it? I know if it can do it in rapid, it should be able to do it during machining. Because, like I said, stepper motors get weaker the faster they go. So that makes it kind of simple. If you can dial your stuff in and still do a reliable rapid, you should be good on machining, unless you're really doing some hogging. And we all know these little machines aren't going to hog. In other words, I will not be partaking in the chip fest that Tom and Adam have going on. And then again, you know, Keith will just come in with this Mongo 4-inch bit and just take off, you know, 3 inches at a time and tell us all to go to the back of the bus. Okay, so now I got a lot less slop. My table is mostly parallel. I'll probably get more predictable results. So that's the mechanical things of it. What can you do in the controller? Well, in the controller you can of course punch in your backlash compensation for your screw. You can get really anal and do what's called screw mapping. So you would take your measurements in as fine increments as you like and map that out. So if you've got some thin threads here, you know, hey, these are imports. So you probably have, we'll use a round number, we'll say 1 millimeter ridges or threads, and then over here it's 0.8 and 0.7 and 1.1. Well, that's where your mapping comes in. So if you've got, you know, a little variation here, you map it, you know, one way here, then you map this one for that variation, and supposedly the machine will bump steps to make up for it in that zone, providing you've set your steppers for enough resolution. Okay, what else was there? Yeah, we talked about the backlash compensation. and the stuff. Okay, the other thing Mike might have tried to limit his errors is, I realize he wants to go as fast as possible because he's got a buttload of these to do, so he wants to do that hit and run in and out. So a way to do it is adjust your G code. So take oh hell, let's pop over to the screen there and look at it. Let me move the camera again, because my computer screen recorder is on the main computer and I don't have Mach on there. So we're going to do a quick edit in Mach and change the parameters a little bit and see if well, we know it'll help, but I'll explain as we go along. Hang on. Okay, so we're looking at Mach 3. I'm using a Mach standard mill screen set, so things are a little different. But so here's our code box, and let's just edit that. So this has change that a little bit. This has your basic movements. So this is assuming you're already at your 0, 0, 0 position, or however you set to, or your tool change position, because depending on how you've set up your part. Either way, this is the rapid movement, G0, and that sends your Z and X axis zooming in to, for this example, -2, -2, and that, well, let's get this out of the way for now. Oh, that's right, I can't play with it while I'm in there. Alright. Fine, get out of there. No change. Okay. No, it used to follow. I don't know why I don't do that anymore. I think I broke something because it used to follow along and show me what was going on. And I don't know why it doesn't do that anymore. Well, hell. Anyway. Okay, so this is your movement here, the first line, your rapids. Zooming over and up to the part. Then your next, your G1 is going to be your feed amount, your feed speed to do the parting. And then your G000, which zooms it right back to where we started in this example. So you've got this sloppy table thing going on, but you want to limit the damage you can do. You've gotten all you can out of it. So what you can do is come up to maybe this point on your rapids. Are we still in frame? I can't tell. I've got this camera crap all over the screen and I can't see what it sees. So bring it up to this point and then switch over to G1, your slow feed, and let that absorb and take the momentum movement and slop out of your system, so you sort of sneak up on your final position, do your cut, and then you can haul ass out of there. So that'll just be a quick edit. So we know for this example our -2 and 2 is our final position. So we're just going to edit that. And make that a G1. Now let's just copy this line. Actually, I should just copy it first, but it's no biggie. Okay, so let's make our G0, our fast movement. For this example, we can say, we'll give it 1/2 inch to play with, so we'll do a -1.5, and again, a 1.5. So now it's going to zoom across, and then, well, hell, it's gone. Okay, we're done. Okay, so now it's going to zoom like hell up to here, or maybe up to there, and then slow down, absorb all the, the momentum, push the table up ahead. Now as we're slowing, it's going to lag back and get back into sort of a, I guess, a seated position, and then it'll do its operation and then haul ass back out. So I'm sure you can already visualize this, but to make this a complete stupid time wasting video, we're going back to the machine and we're going to watch how it's done. Because damn it, if I'm going to put it together, you're going to watch it. Okay, so with the new line of code, boom. Okay, now everything's settled in that position. Now you're going to sneak up that last little bit, and that's going to let the table settle in against its drag and such. And now, hopefully, this action creeping into your final area will take out some of the unpredictability. And of course, it does its thing, and then hightails it on out of it. So we'll run that all the way through because let's be thorough. Boom, done. And of course that's a sloppy, bit of code there because I just threw a number in there. I threw 1/2 inch. Well, there's no way you're going to have a 1/2 inch of slop. So say you've got 10 thousandths of slop combined of all your crap, put 12 thousandths in as your buffer, and get right up next to it, creep it in, do its thing, and come out, and that should give you better repeatability. Okay, have I covered everything? Probably not. Well, if not, let me know. Okay, have I gone fast and furious enough for you to totally turn your brains to mush? Because mine are. Okay, the other method. If you've got all your mechanicals as tight as you can get, let's pull back. Oh, that is as far back as I can go. What a cheap ass camera. Okay, got distracted again. If you've got all your mechanicals out, you've got your cross slide as tight as it goes, you've got your compound nice and locked down. That's another thing people forget to do, especially on a precision operation. Lock down your non-moving axes. So if you're not using your compound, CNC, you're not. That's why when I do CNC stuff, I use the thing that I misplaced a little bit ago. I use my solid post block here. I don't need a compound for that because the machine's supposed to take care of that for me. So that's one less thing to worry about. Plus, as far as I'm concerned, it's a lot sturdier. And of course, it's cut down a little bit to make up for this larger tool post. And so that's one variable out of the equation. So if you're still using your traditional compound for your manual from your manual machine, lock it down. You're not using it, take the play out. But Mike still needed his X and Z open because he's going in and out, back and forth, so he just has to get those as snug and nicely fitting as possible. Okay, so we covered that one bit of slop, and that was only in the gibs for the cross slide. If your X-axis, your table, also has a set of gibs which run this way. If they are sloppy, that also puts some twist in things. So how I do it, or how I check it easily, is well, you can't see it because I got the stupid gauge in the way, but this is pretty much behind this screw on the other side. I'm not moving the camera again, you guys are dizzy enough. That's pretty much flat across. So if you put your finger on the joint and you wiggle this across, you can easily feel one half overlapping or underlapping the other. So you can tell right away if you've got play in that. So you just put your finger on the joint back here and wiggle back and forth, and you can easily feel if that's moving. And I'll do the same thing on the other side. Yes, I have a little bit on this side. So I have 4 screws here. I'm going to tweak this one just a teensy bit, and the next one just a teensy bit less, depending on, because that motor is a little bit, is direct driven, 1-to-1 ratio into the lead screw, so it doesn't have any mechanical advantage other than the threads of the screw, and it's joined by a piece of rubber hose because I've broken 2 flexible couplers because I ordered the wrong sizes, and I've just stuck with the damn hose for now. I keep thinking I'm going to get smart and make my own couplers. Yeah. So, I get any play out of that? Yes, I did. Can I still move the damn thing? Yes, I can. got a little drag on it. Also, you people getting into this and you're doing like I am, a half-breed, we'll call it, hybrid, whatever, or you're using a CNC and a manual machine and you like to have your manual controls, your motors do create electricity. They're little generators, dynamos. So when they're turned off, they're still connected to the controller and they're still generating voltage or power on its lines. And then at a certain point it's going to build up as you're turning to where the motor driver back in your case there is going to put a stop to it and short the two leads together. And that's just like shorting out the alternator on your car. It's going to go to a halt and burn your belt off, which is what happens here. So if you turn this baby too fast to the point where the back EMF builds up, it locks up. And you think you've hit I mean, it's a hard lock. It's just like you think you've ran into a tool or a mechanical obstruction. Well, you just wait for a second for the voltage to bleed off and you can turn again. I hate to do this on purpose because I do so much on accident, but okay, I'll turn fast. Boom, right there. Wait for a bit, start turning again. You just got to remember to turn that slower. So, right there. Wait, let it bleed off. I'm still working on a way to reliably disconnect the motors so I can run any access I want individually and manually. The problem is the controllers, the drivers. You have your controller, which sends the pulses. You have the driver, which takes the pulses and then beefs them up and then pulses the motor. So that driver piece inside, which is one of the more expensive parts, is usually built on JFETs or MOSFETs, and they're really sensitive to just about everything. You sneeze and you can burn those out. And because they're so sensitive, you cannot disconnect a motor while the unit is live. And I'm not even sure if it's safe to disconnect it when it's not live, at least for a long enough period until the voltages and static or what have you has bled off. So I'm still working on a method, and I really hope if somebody has worked that out, please tell me how you did it. Because ultimately I would like to be able to flip off an access, which I'm assuming will remove the power from the driver, bleed it off, and then disconnect the wires to leave those open so I don't get any back EMF and drag on the motor rotor. And then I can use these in a manual fashion in a quick enough time after flipping a switch, and then flip it back on, turn it back into CNC control. That's what I do with the switch over here, but that hits all the access. It basically just shuts off the drivers. And because you can't just shut off the controller, because when the motor driver is in idle, it's sending a lock command. Your motors are locked. So flip it on. There, my motors are locked. So I can't do anything. I have to fight the motors past their steps to do anything. Well, that's not good. So I'd like to be able to do that individually, safely. And I also have a manual motor pulser. I guess they call it a stepper tester or something like that, where you can adjust the speed and have a start-stop and a back and forth. So if you want to just use it as a manual screw, you know, for feeding, because I did all this because I don't have change gears. So if I wanted to do a feed, say on the x-axis, I can just, you know, ramp it up to 30 pulses and just hit go this direction, and I can do face cuts all day long without having to go back to the machine and type in MDI commands, or remember if I'm in lathe mode, do I use diameter measurements and, you know, ×2 or what have you. So I like to have manual and semi-manual. Fully automatic, if you've watched mine. Actually, I don't have my stuff posted yet. If you watch Mike and some of the other new CNC guys, you'll see it's a big adventure of tool crashing and machine breaking and all that fun stuff. Anyway, I think I've rambled on enough, and I hope you've gotten something out of this. So rigidity is key. Your waste slop is the most important. Your screw slop is the next important. And then try to weed out what you can with backlash compensation. Although I do find a lot of instances where I just don't like running it because of the delay, and that's a whole chapter of crap you have to play with to get that to work right. I think I've addressed everything I saw in Mike's video, and it's nice to see. I think he got it worked out. But the mechanics involved, I just hope you you understood what I said, and if not, well, drop me a note, and I'll see if I can make it even worse. So, until next time, take it easy, have fun, and remember, don't get mad, get medieval.